Okay. Hello, everyone. Thank you for joining this course on Introduction to Reinforcement Learning. And this is the first video of the course. In this, I will introduce the basic concepts of reinforcement learning and how it is different from the other types of problems that we see or types of algorithms that we see in machine learning. So before I go into the content, I would just like to include a few acknowledgements. Most of the contents of these slides are based on a video series by Professor David Silver and from the reference textbook for this course, which is Reinforcement Learning: An Introduction by Sutton and Bartow. The material of this class is available online, including the slides and these recorded videos. So that can be accessed from this URL provided here. Okay, so let's get started with the content. So before we get into what is reinforcement learning, it's better to get like a bird's eye view of how reinforcement learning fits into the whole domain of machine learning. So for that, we can divide any algorithm in machine learning into certain classes of learning problems. So one such class is supervised learning. I think all of you might have seen supervised learning examples around, and it's the most common type of algorithms that we use. So in supervised learning, the data is X, which is the input data, and Y, which is a label assigned to the data. So the whole objective for supervised learning is to learn some function F, which maps from this input data and output some label Y. So a good example for supervised learning is image classification. So in this example, let's say we are given images of cats and dogs. If we pick up one image, it could be an image of a dog, then the machine learning model takes this image as an input, does some processing, and outputs the label as either a dog or cat, right? So that's a typical example of supervised learning. Now, the other class of machine learning algorithms is like unsupervised learning. So in unsupervised learning, we only have data X. And there is no supervised or label information available. And the objective for unsupervised learning algorithms is to learn some underlying structure of our data. Now, typically we can think of this as trying to model some probability distribution of how the data behaves, right? So if we look at the different types of examples, one example of unsupervised learning is clustering. So let's say if we have a lot of samples, we have a lot of images, and we don't have any expert labels available, we can apply a clustering algorithm like k-means clustering to define some cluster of images within the whole data set. And probably what might end up happening is we could get one cluster of images which are dogs and one cluster of images which are cats and so on. So this is another class of machine learning problems. Now that we have seen the two different types of problems, reinforcement learning is its own class of problems within machine learning, and it is quite different from supervised learning and unsupervised learning. So in reinforcement learning, we usually have three variables, which is like states, actions, and rewards. So we can think of some agent that can interact with its environment. For example, we could have a cleaning robot which is present in a household setting, and the robot can move around and clean the floor and interact with the environment. So the state for the agent could be where the robot is currently in the room. The action could be where the robot is headed, whether it's going straight, whether it's turning left, whether it's turning right, and so on. And the reward is some measure of how the agent is doing, right? So for example, initially, if the floor was very dirty, at the end of the cleaning session, if the floor is clean, the robot has done a good job. On the other hand, if the robot is colliding with the objects, destroying the furniture and making it more dirty, then it did a very bad job. So the reward that the agent receives is some measure of how well the agent is doing. Now, the goal for a reinforcement learning algorithm is to make the agent pick actions such that the total reward that the agent receives is maximized. So in the case of the robot example, we want the floor to be as clean as possible without destroying any furniture in the room. So reinforcement learning has a lot of examples. Historically, it has been used a lot in inventory management or power plant optimization and things like that. And with the recent trends in deep learning, it is being used increasingly for robotics and self-driving use cases. So that's sort of an introduction to reinforcement learning. Now, before we go on to a more formal definition for reinforcement learning, to better understand this concept of an agent interacting with the environment, let's do a thought process, right? So I want to ask all the viewers, assuming most of you are students, how you have come to college today, right? So now please take some time to think about this question, right? So now let me try to give one example, right? So today even I'm in the university, so I had to travel to the college. So how I travel to the college is like, first I had to get up and get ready, and then I am in my house and my goal is to reach the college, right? So the first thing I have to do is to go down to my car and then make sure that the car is working fine, and then get into the car and then navigate to the college. And so while I'm navigating to the college, there can be multiple possible routes. Some routes have more traffic, some routes have less traffic. Some routes can be completely stopped because of some repair work and so on. So I have to find the best route to navigate to the college. And then once I reach the college premises, then I need to find a parking spot. So maybe some parking spots might be full, some parking spots might be empty. And so I need to find the right spot, park there, and then go to my room, right? So when I'm explaining this example, right, you might have got a feeling that there are multiple decisions that I'm making along the way. And every decision that I make is somehow affecting how well I reach the college. For example, if I chose a very busy route, then the time it takes for me to reach the college would be longer, which is a bad scenario for me. So, what I want to emphasize from this thought process is humans can also be thought of as agents, and humans are doing such sequential decision making processes every day. And if we take the example of me traveling to the college, the first time I came to the university, it took time for me to reach the college and to get used to the campus, where to park, and so on. The more often I do this, the better I get at doing the task of coming to college. So there is some learning process that is going on in my mind so that I can travel to the college faster. So what I would like to say here is humans also use reinforcement learning to make better decisions over time and get better at doing the task at hand. Okay. And throughout this course, there will be different places where we will try to connect how humans behave with how we design algorithms that can actually run on machines. So let us move forward. And now let's have a more formal definition of reinforcement learning. So whenever we are talking about reinforcement learning, we have an agent. An agent is some entity that can interact with the environment. So when I say interact, so what we have is some action that an agent can take. And whenever an agent takes an action, it will receive some reward and some state as a feedback, right? or rather, if we flip it, at every time step t, an agent is in certain state and has received some reward for its previous action, and based on this information, it takes the next action, right? So this is how we can formulate an agent. Now, a reinforcement learning problem requires an agent, but it also requires an environment, right? So once we have an agent and environment, so at each time step t, the agent receives some state and some reward as input, and the agent takes some action as a result, right? As an output. Now, the environment, on the other hand, receives this action from the agent. So the agent does some action in the environment, and the environment reacts by giving a new state and a new reward, right? So one thing to note over here is, once the agent takes an action, the environment updates the time step t to go to the next state and the next reward. So this is how an agent and environment interact together in a reinforcement learning setting. Okay, so now let's look at an example of how it actually behaves, right? So let us say if we have a grid world setting like this, the task over here is, every time the robot spawns in this blue cell, and the task is to navigate through this grid so that it can reach the goal cell. So that's the task for the reinforcement learning problem, or for the agent in this particular example. Now, because we have defined an RL problem as having states, actions, and rewards, so let's look at states, right? So every possible cell in this grid world can be considered as a possible state that the agent can be in. So the robot has to be in one of these cells, and it cannot be in any other cell apart from these cells, right? So what I have done over here is, for every cell in the grid world, I have assigned some index S0, S1, S2, and so on. So this particular environment has 26 possible states that the robot can be in. So now the robot can try solving this grid world multiple times, and in every instance there are multiple time steps. At every time step, the robot has to be in one position in this environment. So in this particular example, the robot is in state 15, or this particular red cell. So now let's look at actions, right? The robot can be in any particular cell of the grid world. In every cell, the robot can either choose to go north, can go south, east, or west. So for every state in this grid world example, the agent can take one of 4 possible actions. So these 4 actions are the action space of the robot. So now let's define rewards, right? If we assume the robot to have some battery inside, right? So the longer the robot keeps moving around in the environment, the more the battery gets discharged, right? So to show such an behavior, we can define a reward function such that as long as the current state of the robot is not the goal state, it will keep receiving a reward of -1, which indicates its battery is discharging. And then as soon as the robot reaches the goal state, then it receives a reward of 0, indicating that it has reached the goal and its battery won't recharge anymore, or it won't discharge anymore, right? So this is one definition of a reward function. And the key point to note here is, there can be different types of reward functions as well. For example, we could have defined a reward function where we take the goal state and try to calculate how far away it is from the goal state, and based on how far away it is from the goal state, it can receive a larger reward. So what I want to emphasize here is, a reinforcement learning problem can have different types of reward functions, and that's a representation of how you want to train the agent. Okay. And the last thing that I want to cover is the environment. So in this grid world example, the agent can take actions, but the environment can also respond. For example, if we think of this as state S1, right? If the agent takes an action of west, right? So it can transition to state S0, right? But let's say if it is in state 1 and the agent wants to take an action to go north, because there is a wall over here, um, whenever the agent tries to go north, it will hit the wall and then come back to the same state again. So some actions will result to a valid state transition, but then some actions, because of how the environment is restricted, it might come back to the same state again. So the environment can also respond to what the agent takes as an action. Okay. So now that we have defined the whole example, there is a concept of episode. So what we mean by episode is one trial of the agent trying to solve the task. So, and for every episode, we can define something as the return, which is the total reward that the agent gets throughout the episode. So, what we see over here is one example of an episode where the agent traveled south and then kept traversing over here until it reached a reward of -30, which is when its battery completely discharged and the episode terminated, right? So this is one example of an episode where the agent interacted with the environment. And another example is where the agent takes the shortest possible path to the goal and it completed the entire task in 15 steps and it can receive a reward of -15. So this is another example of an episode. So whatever we have defined so far, like the states, actions, rewards, environment, and episode, can be defined for any other problem that we want to solve with reinforcement learning. And this is the first step that needs to be done before we actually design an algorithm to solve the problem. So now that we have done a toy example and defined the states, rewards, and actions, let's look at some real world examples. So what we see in this image is like a investment banker who is trying to invest in stocks, right? Now, it is possible to treat this problem as a reinforcement learning problem. So now, if we were to think of this as an RL problem, we can think of the state as the current value of the stocks, right? Or let's say the latest news. And the action is the agent can choose to either buy the current stock that it's holding, or it can choose to sell the stock that it's already holding, right? And the reward can be whatever profit or loss that the agent makes at the end of the day. So let's say throughout the day, if the agent makes like 10 to 15 transactions, where some of them are buy and some of them are sell, and if the total net worth of the portfolio is more than what it was the previous day, then it has a positive reward. Or if it is less than the value from yesterday, then it's a negative reward. So this is how we can define portfolio management as an RL problem. Let's look at another example, right? So if we are talking about self-driving car, right, it is also possible for us to define the state, action, and reward. So can you think of what the state, action, and reward can be? Okay. So in this example, the state can be what is the current position of the car and what's the current acceleration of the car. The action can be either pressing on the accelerator and speeding up further, or it can be to press the brake and then stop the car, right? Now, we can also define a reward function for this example where as long as the car is driving on the road safely and not hitting any of the objects, then it can keep receiving a positive reward. But if the car is driving off the road or it collides with another car or hits a pedestrian, then it's a negative reward. So it is possible to train a agent to drive a car by formulating it as a reinforcement learning problem. So now that we have given some basic definitions, let's formally define what is the problem statement, right? So if we have an agent and if we have defined the states, actions, and the reward function, then the goal for the agent is to select some actions to maximize its total future rewards. So the problem over here is an action that an agent takes can have very long-term consequences, right? So we can think of board games as also very good examples where reinforcement learning can be applied. So if you're talking about chess, right? Maybe some of you play chess. And what you might have noticed is, let's say if you make some move right now, it might be a good move, it might be a bad move, but whether it's a good move or bad move can be decided multiple steps later when you actually end up losing the game, right? So one problem with reinforcement learning is this long-term consequences that actions can have. And because of this, the agent needs to have the planning ability so that it can sacrifice some negative rewards for now so that it can get much bigger rewards down the line. So for the example of chess, we can choose to sacrifice a piece right now and then win the game eventually, right? So this is one planning ability that the agent needs to have. So as I explained here, right? So the same thing also applies to portfolio management. So maybe we might end up getting some losses for the immediate few days, but if we stick around and stay with the particular stock, we might get much bigger long-term rewards, right? So this is one ability that an agent needs to have. Now, let me cover a few more characteristics of reinforcement learning. Usually in reinforcement learning, there is no supervisor and there is only a reward signal that is available for the agent. So if we were to contrast the two examples, and if you're talking about an agent or a person playing tennis, then in this example, there is a coach who is showing how to hit the ball and exactly play the game, right? So this is the supervised learning setting. But in reinforcement learning, typically what happens is there is an agent who is just playing the game. Like for example, here, this player is just hitting the ball to a wall and just seeing how the ball interacts and learn how to hit the ball better over time. So this is typically what happens in reinforcement learning. Another characteristic of reinforcement learning, as I mentioned before, is the feedback is not immediate. If we take a bad action now, we can actually get a negative reward multiple steps later and not immediately. And the last thing about a very important characteristic of reinforcement learning is the concept of time is very important. So the agent has to take multiple actions over time to solve a task. And at which time step, which action is taken is very important, right? So for example, if we take this scenario where a robot is trying to climb a hill. So in this particular state, if the robot chooses to go extreme left, what might happen is it can lose its balance and actually fall off the mountain. On the other hand, if the agent chooses to take a slight left at every turn, then it can actually navigate the task and complete the goal, right? Or climb up the hill. So every action that an agent takes at a particular instant of time has a very significant effect, and it can lead to a difference between either solving the task or completely failing at the task. So these are a few characteristics of RL, and overall this is an introduction to the reinforcement learning course. So in the later lectures, we'll start looking at more formalisms and then eventually start looking at different algorithms to solve reinforcement learning problems. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.